Before we begin, I would like to remind everyone to kindly keep your microphones muted. And also that we will be recording the session. Okay, so today we have Assistant Professor Hao Tang from the Department of Geography at NUS. Dr. Tang's research is centered on the remote sensing of the environment with a focus on the use of satellites for mapping and monitoring forest dynamics under a changing climate. Prior to joining NUS, he was a remote sensing scientist at University of Maryland and served as principal investigator and co-principal investigator for multiple NASA research grants. He is also a NASA Earth and Space Science Fellow. Dr. Tang is on the science team of NASA's Carbon Monitoring System and is a science team member and product lead of NASA's Global Ecosystem Dynamics Investigation, or GEDI mission. The GEDI mission is the first high-resolution LiDAR mounted on the International Space Station and is utilized for measuring the Earth's forests and topography. Dr. Tang's talk today introduces us to this novel technology for Earth observation and discusses some of its potential applications for nature-based climate solutions with a focus on forest ecosystems. We will first hear Dr. Tang's talk before proceeding to the Q&A segment in the last 20 to 25 minutes of the webinar. If you have any questions for Dr. Tang, you may either unmute yourself or raise your hand through Zoom and proceed to ask your question, or you may type your question in the chat box, which we can then read for Dr. Tang to answer. Okay, so now I'll pass this to Dr. Tang.
Thanks. Thanks for the intro. Just give me a minute. I'm starting to share my screen. Can you see that?
Yes, we can.
Okay.
All right.
Sounds good. Thanks, Don, for the introduction. That's very nice of you. So today I'm going to talk a little bit about the work I've been doing in the past 10 years. I would say that. So even though I call it an introduction to GEDI Ecosystem Lidar, I believe it has many relevance go beyond the GEDI and the ecosystem and the carbon. And hopefully you can enjoy this and we can have form more discussions afterwards. And as Don has introduced, I'm a new faculty here at NUS in the Department of Geography. Before that, I was at University of Maryland, working most closely with NASA. And for GEDI, I've been starting with that for quite long and witnessed the entire development of GEDI. And this cannot happen without the efforts from the PI, from NASA Goddard Space Flight Center, and also my colleagues from Brown University, Northern Arizona University, US Forest Service, and a couple of others. So carbon, right? This image, I'm sure you see this at different locations and different versions, and we are all kind of very familiar with this. So we know the biggest problem we're facing right now in terms of climate change is the increasing amount of CO2 in the atmosphere. And we know very well about the dominant source of that, which comes from the fossil fuels and the industry. And we also have a pretty good idea about the amount of the carbon increase in the atmosphere and the amount of them deposits into the ocean. But we have a major problem over the land component. Part of the problem is because it is a two-way traffic. On one hand, we have the land, especially the forests, absorb a huge amount of carbon from the atmosphere. But on the other hand, we've been witnessed huge and drastic changes in land cover and land use. Like so for folks living in Southeast Asia, and if you look at Indonesia and Malaysia, that's the most pronounced land cover land use changes a hotspot. So that makes things a little messy, right? If you want to know, saying how much carbon we actually have, or the carbon flux over the land component, we probably need a good idea about where we gain the carbon and we will lose the carbon. And that's more an area-based approach. The recent development in satellites has really promoted this, I would say, discipline and resolved a lot of the uncertainties and ambiguities from global perspective. On the left bottom panel is 30-meter resolution data product updated annually from Dr. Manhansen at Department of Geography at University of Maryland. So what it shows is annual change of the forest carbon, forest area from the early 2000 to now. So we show both where we have intact forests highlighted in the green, and we see where we have lost carbon in the red area and the gain carbon in blue. And the purple line indicated we have both gain and a loss. But that's not the end of the story. We don't even know the stop yet, right? So what do we only know by now is where we know there are dramatic changes in terms of forest area, but we have no idea about the amount of carbon actually being lost to the atmosphere or being absorbed into the land. And we have a huge uncertainty associated with that. You can imagine the amount of carbon content, saying in the tropical rainforest, is not equal to those in the Tegatron in the boreal region. And just by equaling the areas, not giving the correct balance at both ends of the equation. But how well does the remote sensing do, or the satellite do, when we measuring the carbon density? Probably not so well, especially over the high end. So if you look at the images on the right, if you follow my cursor here, at the low end, probably less than 100 megaton per hectare or ton per hectare. Satellite seems to be okay, either using the passive optic sensors or the radars. But once go beyond the 150, we have a terminology called signal saturation, meaning that regardless of how hard you try to get out of the satellite, you'll not be able to really detect the high-end changes. And that's problematic, especially for the tropics, because we know here, we would either expect the forests to have a biomass more than 300 megaton per hectare. And now I'm telling you that using conventional method, we don't know how well we can measure that. That's going to be a huge problem if we want to turn this into, saying, the carbon critics or the nature-based solution. But is there a solution to this problem? The answer is yes. This is kind of a universal relationship and probably the state of the art of measuring the biomass in a forest. Its relationship with the height or the 3D structure. So as clearly shows in this little figure here, as the vegetation starts from pasture all the way to the primary forest, it increases in carbon or the biomass, but also increases in height. And they have a very good relationship with each other. And that forms the fundamental basis how we can actually accurately determine the amount of carbon in the forest. And that prompts the topic of the day, LiDAR remote sensing. LiDAR remote sensing is an active remote sensing technology that uses a laser pulse to measure the distance to a target. This little animation made by the NASA Goddard Space Flight Center shows the basic idea. You mount a laser pulse on a platform, shooting lasers downwards, take the timing and convert it to the distance, and get a bunch of different pulses aggregated together. And you have this very nice, cute 3D point clouds showing on the right here. And you can do a little bit more classification based on this point clouds, such that we know, for example, on top of the trees, you have the first return, and they have multiple returns until it hits the hard ground, which presumably represent the ground. And it can resemble the 3D structure. And that is exactly what's needed for high precision carbon monitoring. And this, as I just mentioned, the laser sensors can be mounted on different instruments. Arguably, the most precise or most data intensive measurement will come from this, the terrestrial laser scanning. On the top are one of the laser scanning made by Cicero in Australia. And here's the image from Interior National Forest by Alan Stratton and Chris Shah from Boston University. Have a cute name for this little instrument called Echidna. And on the bottom panel, that's from the result from the modern industry, and it's from one of the regal terrestrial laser scan. And here we can easily identify even individual trees and the leaves and the branches and stems of that. In fact, we have such huge amount of data that people need start to decimating the data a lot and trying to get like just a few geometric parameters to represent the forest. And on the right here, I'm just giving you an example. This is a 3D reconstruction of the forests, probably the tallest tropical tree found in the Danang Valley of Sabah, using the TOS as a reconstruction. Airborne LiDAR is arguably the state of the art for large area carbon mapping. It presents the most accurate 3D structure for the canopy and for the ground. But it comes as a problem, a prohibitively high cost. Right now, the exact number can vary a little bit, but generally it will cost more than $100 per 1 kilometer square. And if you multiply the area, that can be very, very high, and not many projects can afford that. Also, it's subject to operational restrictions due to different weather conditions and et cetera, et cetera. And also, since it requires high accurate geodetic measurements, the data sharing can be problematic. And sometimes it's just not be allowed to share between different agencies within the same government. For example, over the Amazon rainforest, for example, the Brazil government would not allow any of the US flights to collect airborne LiDAR data there. So, and I would argue that the Amazon forest is probably the most widely studied and influenced by the airborne LiDAR data, but still to date, it has only very limited efforts compared with the massive amount of area of the Amazon rainforest. And here I'm just showing the red rectangular and KMD files representing where the airborne LiDAR data has been acquired. You can see they are only a tiny fraction compared with the entire Amazon, not to mention even within this 80-kilometer tile. Same story happened in US, presumably the leading country in terms of airborne LiDAR data acquisition. What I'm showing here is kind of little data dots here, if you can see. It's little tiny dots, polygons here. These are the the projects funded by NASA's carbon monitoring system with a forestry-focused LiDAR. That's very limited. The green line here shows this the topographic LiDAR acquisitions. Even though they've been able to capture the 3D structure to some extent, but they are definitely far from ideal for forestry or carbon purpose. But we're still working on that. Having said that, there's nothing can compete with a satellite in terms of solving all the problems I've listed there, right? It's a relatively low cost compared with the airborne LiDAR data, and you don't have much of the restriction in terms of data or the operations. This is just in the sky. And that's what we've been doing. And that's what NASA has been doing. Indeed, GEDI is not the first LiDAR for 3D measurements. We have ISAT-1 launched in 2003, and GEDI also has a big sibling, ISAT-2. But as a name probably can tell, it focused more on the polar region, with a focus on the ice sheet dynamics, which is equally important for the climate studies. But GEDI is the first high-resolution ecosystem LiDAR, with a focus on the Earth's forests and the topography. This is GEDI's goal. GEDI tries to advance our ability to characterize the effects of changing climate and land use on ecosystem structure and the dynamics. Has two major deliverables or the targets, the carbon cycle and the biodiversity. Some of the key facts about GEDI: it was selected in 2014 for $94 million. It's deployed on the International Space Station, Japanese experimental module exposed facility, launched on the launched onto the ISS on the SpaceX CRS-16 in December of 2018. It was presumably to be a 2-year nominal mission length, and the first data release to the public was on the November of 28th last year. Here I'm just giving you a quick key mission milestones of GEDI. On the top left panel, that's the engineers trying to assemble the GEDI optical bench in the clean room. So the size of GEDI is about the size of the refrigerator in your home. And you can see here, that's the 3 lasers, the one hiding in the behind, and the 3 star trackers on top of the optical bench. And the lasers on, and I always love to show some of the SpaceX orbits, just looks beautiful. And on the right, that's the ISS Dragon extracts the GEDI from the ISS robotic arm extract the GEDI from the Dragon trunk. The telescope is about 0.8 meter, and that's actually a backup of the ISAT-2. And for that, that saved us $1 million. So as planned, the GEDI should have ended its mission by now. That's kind of an official plan. But since the NASA headquarters recognizes such an important mission, has contributed so much to the community, that it decided to have another 2-year mission extension. And that's been confirmed already, meaning that in total, we're going to have 4 years of observation on the International Space Station. Here, I'd like to show another animation from Goddard Space Flight Center. This is the International Space Station. So we have a zoom in into the Jamie EF, and that's where GEDI is spotted. There are also other missions. By the way, there are also other missions in parallel to GEDI, EcoStress, History, some developed by other space agencies, and together they form a fleet for the Earth observation and for the vegetation. So the GEDI shoots down with 3 lasers and using techniques to split it into 8 beams. Around each of the beams, GEDI shoots consecutive lasers downward. And here, this is one of the key GEDI outputs, a waveform over a footprint. That's what we call equivalent to a plot. And here we show the laser energy captures the entire profile of this vegetation here. And the energy shows the amount of the leaves or the foliage material within the illuminated area. And on the y-axis, as a signal can tell, you wouldn't be able to know how tall the forests are. Here, I would like to cover some of the fundamentals of GEDI, and it's very important to review. I mean, to date, the biggest misconception or query about GEDI is still like this. For example, how does the point cloud of GEDI comparable to your airborne LiDAR data? Or what's the spatial resolution of GEDI? Even though the trend is declined, but still not completely gone. So that's why I want to make more clear. The only thing GEDI really measures is the amount of the laser energy reflected by the plant areas at different heights above the ground. That's it, period. That's all GEDI measures, the black lines here. It's not the beautiful 3D point clouds you commonly see from airborne LiDAR data. And through this process, the loss of 3D point cloud is permanent and irreversible. It means GEDI is not error-free relative to conventional airborne LiDAR data survey. And this is the first implication of the loss of information from full 3D point clouds. So that's some kind of, if ever you forgot all what I've been talking today, this is probably something you should remember. But that does not prevent us from using GEDI, which I'm going to introduce in the following slides. And also, GEDI is not spatially continuous. What we have is a series of 25-meter plots. You can imagine the yellow dots showing here. And we have multiple satellite tracks. And when stitched together, we can generate in the statistical matrix at regular grades and nominally at 1 kilometer scale. And here I'd like to show the ground spatial configuration again. We have 3 lasers, and down to the ground, we have 8 ground tracks. And with each of the ground tracks, we have a series of 25-meter footprints separated by 60-meter along track. And across tracks, they're separated by 600 kilometers. Oops. Something's not working. Okay, there we go. Something just messed up on my screen. Hopefully it doesn't impact anymore. The GEDI data products, I guess this is the key, right? Everybody wants to make use of the GEDI products. Just as I introduced, the only thing that GEDI really measures is the waveform by itself. And then we assign the geolocation information of it. So we basically know where it's gonna hit on the surface. And on top of that, we have a little bit more interpretation of this waveform. And we can know where the ground is, where the top of canopy is, and that gives us the topographic elevation as well as how tall trees are. In addition, we'll be able to use the energy information to differentiate between the canopy and the ground, and using that to generating more biological meaningful variables such as canopy cover, leaf area index, and vertical profiles. For example, this one shows the amount of the foliage distributed along the y-axis. So we know how much leaf you would have at each height interval. And that's going to be very useful for the carbon cycle and analysis and a lot of demographic studies and biodiversity. There are a couple of the GEDI-related products I would like to introduce before I jump into the biomass or the carbon components. So to start from the very left here, which is the land cover based products. So we have an idea about the past changes using high resolution satellite imagery. And then in the central one is one of the initiative led by Sean Haley from US Forest Service, basically align biomass inference using the statistical approaches to customize the amount of the carbon we have. And on the right is the ecosystem demography model that can help us predict how much carbon we'll be able to absorb in the future. So together, it can inform us about the carbon dynamics from the past into the future. The biomass, the GEDI's L1 mission requirement. So I'm just going to read this. So acquiring LiDAR canopy vertical profile to estimate above ground biomass density for the Earth's global tropical and temperate forest, less than 1 kilometer resolution. And at the end of a 2-year mission, at least 80% of 1 kilometer cells shall be estimated with the precision of standard error of the larger of the 20 megaton per hectare, or 20% of the estimates. This is our mission requirement or mission goal. And this is built upon several of the mission requirements and operations. The first is the mission operation. That means how we be able to acquire data and configure spatial distribution. It's not easy. It's a daily routine work we've been doing every week, and assembling information to make decisions where we want to acquire the data and where we might have the problem. And also subject to the instantaneous acquisition and pre-processing. That's more like a heavy duty work and being done internally at Maryland and the Goddard Space Flight Center. The focus of the talk today will be on the biomass model development, and I'm going to show it in the next slide. This is the most conventional or the classical way we estimate the amount of the biomass in the forest using airborne LiDAR data or any kind of LiDAR data. So we'll flow the airborne LiDAR data, collect the field data, field samples under this, build a model, and estimate the amount of biomass and uncertainty. And all it's built on top of this assumption or the equation here, the anamorphic equation. We would assume that above ground biomass is proportional or equal to some of the height metrics or some of the conversions of that. And here's, we would assume that's kind of the one of the field data we have just collect there. And you can also imagine that could be one of the GEDI shots, right? But there are a couple of the problems in practice when we want to do it from space. And the first and foremost is the geolocation error. You would assume when I lay the shooting down and I scramble all your field gears and trying to measure the amount of the carbon illuminated by GEDI. But in practice, the GEDI shot might not be where you think it is. This is the fundamental challenge when you work with the space mission. And you cannot do that in a timely fashion. It requires a lot of post-processing to make sure you get to the right place. And that takes time to do this, usually 2 years or even more to make sure all the orbit, all the pointing are correct, and such that we'll be able to bring the geolocation error down to less than 10 meters. And here's an impact of if you have geolocation offsets of 10 meters. And over the tropics, for example, in the civil biological station, you would expect a height error about 2 or 3 meters, and that's huge. Therefore, we're using a GEDI simulator to conquer this problem. What the GEDI simulator does is taking the instrument's configurations and the airborne lidar data and the corresponding field data. And I'm simulating where the GEDI should look like if it is everything being perfect. That effect get rid of this geolocation effect, and then we can generate GEDI equivalent parameters and develop a model and propagate our uncertainty. That's the whole idea about how GEDI is intended to measure biomass. To do that, GEDI builds a forest structure and a biomass database by assembling co-located the airborne lidar data and the field data and generating equations to that. This map shows a global distribution of our database to date. So it is predominantly distributed in the United States, North America, South America too, some in Africa, and a lot of in Europe. Australia is well covered as well. Southeast Asia have a couple of limited sources, and we have a big gap in East Asia. For developing this database to get a robust global representative, we have two major transferability or the model assumptions we have to make. The number one is the geographic transferability, meaning that models can be extracted to locations outside the geographic extent. And the model transferability points to whether the data signal from the simulated data can be effectively translated to the real GEDI data. And that's some ongoing efforts within the GEDI team right now. So here, just give you a first quick overview about this stratification scheme to address the transferability issue. So here, GEDI approached two different stratification schemes here. Number one is based by plant functional type, and number two is based by region. And a combination of these two is used to generate the first version of GEDI L4A footprint level biomass density, and it's already publicly available. So you might want to take a look using the link down below. So on the right are the table panels showing the amount of the footprints we've been using to derive the GEDI biomass. And here I'm just highlighting where the biggest problem might be. On the column, EBT represents evergreen broadleaf forest. You can see that the Africa and the South American has a way more data compared with the South Asia and Southeast Asia. So more than double of that. And on a XX on the rows, the biggest data gap, as I mentioned again, is in the Asia component. This is GEDI's mission timeline. Just give you another kind of quick view about the data release. So the first data release being already done, and we're also being releasing data in a monthly manner. And by now, we've already released the first 18 months of data, and presumably the observation of GEDI should have ended in April of 2021, and everything should have been closed by now. But as I mentioned again, like the headquarters agrees to extend the mission to the 2023, so it's kind of good, a very good relief for our team, and we'll be able to continue to provide more data to all the community. And here I would like to provide a quick view of some of the data products. The first one is the GEDI bare Earth elevation data products. You might not be surprised by any kind of satellite observation anymore these days, since you are familiar with different of the maps generated. But I will tell you, this is the first map to show the elevation of the ground surface underneath the dense canopies. The first time we've been able to do that. You might say, well, we have some of the historical ones, such as the SRTM, DM, Canopy X from the east side, etc. But indeed, they are not really being able to measure the ground. Here's one of the example over a peatland in Brunei, for example. The red is the GEDI ground elevation measurements, and the SRTM as a C-band reader and a Canopy X-band reader is somehow measuring something in between of the top of canopy and the ground. That's due to the nature of the reader. They are kind of using this phase center to determine where the scattering is concentrated, but not that precise in terms of the ground elevation. Also, another example of Mountain Everest. This is kind of one of my favorites, and I believe this is any mission being able to do to the best of their extent. So we're very, very close on top. But if you ask me how exactly the elevation is, I have to say, well, I can't tell you the exact number, but it's probably greater than the 47.78 here. For its canopy height, of course, this is one of the major deliverables, and everybody will want to have that. And just for your information, this is one of the tallest tree ever been measured by GEDI, at least in my own bookkeeping. So in the northwest coast of the United States, the redwoods, it's more than 100 meters tall, captured by GEDI very well. Also, GEDI is the first mission be able to measure the high canopy cover component. I mean, this really high dense canopy in the tropic forest. If you walk in the woods and take a look upwards, the amount of the sky you'll be able to see is kind of the 1 minus the canopy cover. And these are really important indicators about the species richness and abundance. Now, and I'm leading this part in the GEDI mission, which is the vertical profiles of the leaf area index, basically. This animation shows from the ground to the top of canopy, the amount of foliage distribution. And it can be very useful in addition to just the total saying leaf area number. This is one of the example, not from GEDI, but it's airborne prototype, showing that even though these trees can be effectively having the same plant area index, but their vertical distribution can be contrast to each other hugely. This is one of the example in the Africa. And of course, we have the biomass generations and still in progress, and we're going to deliver the final graded products hopefully soon in the future. And on the right little animation shows how the GEDI accumulates observation over time over state of California. And of course, I can't resist the temptation of showing how GEDI looks over Singapore. I was a little worried that we'll not be able to get enough data over Singapore because of the cloud coverage. So GEDI is an optical sensor too, even though it's active, and meaning it's subject to the cloud contamination. But nevertheless, we made a lot of observations, and on the right is a zoom-in view over Bukit Timah Natural Reserve. I was there a couple months ago, and at the entrance, I think the GEDI is doing a reasonably good job, but even though I haven't taken the measurements myself to see how tall these trees are. It's going to be very close to the final few slides. Here, I'm just showing you the amount of the data we have collected by GEDI. You might have heard about spaceborne lidar for measuring biomass from some of the colleagues or even from some of the prestigious journals. We've been talking about using millions of plots to do that. After 3 months, GEDI has already provided 2 orders of magnitude more than that. So in the beginning, when we're trying to plot them in the same figure, we just feel like we can't do that because previously that's where they are. And that's what GEDI has been doing. And by the way, the 95 and 98 beam sensitivity is the indicator of the quality of GEDI. 98 is presumably to be better than the 95. And now after 18 months of the data acquisition, we have more than 5 billion of good quality shots and more than 3 billion high quality shots. That's 3 orders of magnitude more. And imagine GEDI is going to be there for another 2 years. So presumably you're going to have more than 10 billion really high quality shots of canopy height measurements and a pretty good estimate of biomass. But one thing I have to warn you, that is the high quality GEDI signal or the observation is not equivalent to the accurate biomass estimates. Again, GEDI does not directly measure biomass. GEDI only estimates biomass through allometric equations, and that relies on a build-up of the calibration and the validation data over different biomes or the different stratifications. And to date, the biggest problem is still in Asia. If you read this table, it's still to be refined, but what it tells you is that while GEDI works reasonably well over the rest of the world, we have the biggest problem here. And it's up to us to further reduce this error and make the better product. So to summarize, this, I would say, is kind of a follow-up of the previous slide. I would call this both a challenge and also an opportunity. Right now, the biggest challenge for most of the GEDI users as we're collecting feedback is a massive data volume. To date, we've already distributed about 100 terabytes of data. That has already dwarfed the MODIS data product, if you're familiar with MODIS, which is the most widely used remote sensing product. And also, as I mentioned, we have relatively low performance of Asia, and we need to continue to refine that. One thing I haven't talked much about is about parallel satellite observations from multiple space agencies. And it's not limited to LiDAR, right? We need every resource we have to fight war with climate change, and we should do that. With that, I would like to end in a typical GEDI way. May the forest be with you. And on the right are the data products details if you want to know more. That's all I have. Thank you.
Thank you, Dr. Hao Tang, for that insightful presentation about the NASA GEDI LiDAR and its potential applications. We will now be taking some questions from our audience. Again, you may either unmute yourself or raise your hand through Zoom, and then proceed to ask your question, or you may type your question in the chat box. So, yeah.
I'm gonna stop sharing now.
Okay, maybe I can ask just a starter question, Prof. Hao Tang. So you mentioned earlier that a lot of the uncertainties, for example, like are in Southeast Asia, South Asia. How may we, be able to contribute? Like, what is causing the large uncertainty, I guess, in Southeast Asia, and how may we contribute to reducing that uncertainty in the estimates?
The first thing we want to do is to have coordinated efforts and contribute more the calibration and validation for that. So when we say the uncertainty and errors here, these are the current estimates in the current database. And we need more data to either to test this hypothesis to be true or not. It might be in the end that everything be fine, we're doing an okay job, but right now we just don't know yet. That's the first thing we need to do. And the second, there should be probably more coordinated efforts of airborne LiDAR data acquisitions, and such that we can have a more open discussion and a transparent data framework, and have more data sharing protocols. And to doing a transparent way is very important because we want to make it be transferable not only within the Southeast Asia, but essentially to global, especially when we seek a global kind of solution in a nature-based solution, right? And the transferability and transparency are top priorities of doing so. And if I add a third kind of opinion on top of this, I would say we also want to develop different on-the-ground techniques to improve the observations. And we can't do this alone. Community-based efforts are also important. And in some sense, in the big data era, more data is always welcome.
So you mean, Dr. Tang, so it's not just the airborne LiDAR to help, but also field or forest plot data set will be able to help in the calibration validation of the GEDI LiDAR products. Is that right?
Absolutely. So I always like there's always a kind of a feeling in terms of competitions between, okay, I want to do more field work and I want more airborne LiDAR data. I don't think there should be such of the conflicting opinions. In fact, I think this goes kind of in an iterative way. You would need somehow, for example, the satellite to tell you where the uncertainties is. And then we have like a ground choosing to know if this is really a problem or just some of the artifacts. And collectively, it improves our knowledge state by state.
Okay. So we have I think a question in the chat. I just want to confirm. So there's I wonder if Professor Chang Chung Yo wanted to ask a question. Yeah. Okay. Please, Professor. Yeah.
Yeah. I think I might just ask a question here. Thanks, Hao, for the interesting talk. I get a question about the different level of uncertainty for different products, because I see you guys put leaf area index in L2B and biomass in L4B or L4A. Just curious if there's a different, does that mean like we have more confidence in LAI, or well, what's the reason for that different level of products?
The different levels of product follow the standard protocol of the NASA product development. So usually you would build the higher level data products on top of the lower level. The lowest level of GEDI products is a pure waveform and housekeeping data. That's the L1 level, which most of the non-experts would not make any use of that. I would imagine the major download or the major interest to the general audience was starting from the level 2. L2B, that's what you just mentioned, the leaf area index and a profile. The L2A, that's the component that contains the geodetic measurement of the elevation and also the RH metrics, the height. The L4A, the biomass component, leverages the derivative from the L2A to generate to estimate biomass. And having said that, you are somehow right about the error propagation, because if you have a larger uncertainty at the L2, you would imagine that would be translated into a higher product. But that might not necessarily be the case, because it depends on how the model being built up in the biomass and how robust that is. The model is to different errors.
Okay, so you're saying, kind of understanding this way that the LAI products might have the similar uncertainty as the biomass product.
I would say in general sense, Canopy height will be the most accurate, and then followed by the LAI, and then followed by the biomass.
Okay, great, thanks.
Thank you, Professor Yo. So we have a question from Waykit Lee. So it says, hi, Dr. Tang, thank you for the talk. And could you explain a bit more on how ground truthing or verification was done? I think, yeah, referring to maybe, in general for the different products by GEDI.
I would imagine when we keep asking this question, I would assume you are actually more interested in the biomass component, is it? I've already explained a little bit in terms of the L2 component. The height one, I would say GEDI is doing a relatively good job. In terms of high quality GEDI shots, we would have an error around like 1.5 or less than 2 meters. And for the canopy cover, we would expect to have an error about 10 to 15% canopy cover-ish. That's the same thing with LAI. In terms of the biomass or the common component, the ground choosing is being done in 2 separate ways. One is the calibration, as already mentioned in the presentation. And for the validation components, we're using different approaches of doing that. The predominant one is to fly airborne LiDAR data, especially the large footprint airborne LiDAR data. One of the airborne prototype of GEDI called LVIS. It can provide wall-to-wall observations and almost identical high-quality waveform. So that's one of our major tool to do the validation components. But we also rely on the ground validation as well. And that's being done in 2 different protocols. One is using the conventional forestry survey, that you take the measurements in a plot, sampling the trees of different sizes, measure the DBH, and it converts using allometric equation to estimate the biomass within that plot and related that to the GEDI signal to see how that's doing. And also more recently, the progress in the terrestrial laser scanning, as I showed in the first 2 slides, is kind of a popular tool. So it somehow can create a digital twin, and it's been very useful to develop more precise allometric equations or the biomass estimates from the ground. So that's kind of a 2 parallel efforts going on the ground.
Right. Thank you, Dr. Tang. We have another question coming from Steve Teo. So how large are the uncertainties from other non-height factors like plant functional type, seasonality, compared to the height uncertainties? And how could this affect the biomass estimates?
That's a very good question. So the way we do that is trying to do different stratifications and basically a simulation of different scenarios, and using that to determine how robust our biomass estimate is. So in other words, for example, we will start with a simple model saying everything being the same. Like we just treat all the vegetation on the planet Earth as the same and just apply the equation. That can come up with one equation. Or we can divide the words into small pieces as possible and to apply like different equations. In the end, we're going to compare different models to see what's the overall performance through both stratifications and also bootstrappings, etc., different statistical methods. And in the end, based on the data we have right now, we would conclude, okay, given the facts we've already considered, this is the best result we would have. And of course, it does not prevent us of reinventing the models in the future as we're getting more data and more information. And of course, trying to reduce this uncertainty as much as possible.
Right. Thank you, Dr. Tang. Any other questions from our audience? Dr. Tang, oh, okay. So we have Janice Lee asking, she would like to ask a question. Hi, Janice. Yeah.
Thanks so much, Dr. Tang, for this great presentation. I thought it was really interesting. Yeah, I'm curious to know what are your plans for GEDI now that you're based in Singapore, and then looking into maybe working with people to do some validation, for example. So I'm at the ASC at NTU, and we have the Forest Joe folks who are present here. So I'm wondering also, like, to what extent you're also interested to, consider some of the plots that have been collected, like in terms of biomass plots that have been collected in terms of the data sets in this region. And just curious to know, like, yeah, what some of the future plans that you might have to work on GEDI, since there's such a big gap in data.
Yeah, that's right. I'm glad you brought this question. So I'm sure there are a lot of things to be done, since, as I mentioned in the last slide, it's the challenge and it's the opportunity, right? If it's being perfect, I should just be fired immediately because there's nothing left for me to do anything. But having said that, I would say the first thing we do is still to pursue a validation. Just know where we are in terms of status. Right now, just given the insufficient data acquisition, we simply do not know outside the database we have right now. And in fact, NASA and the GEDI team is considering launch a Southeast Asia campaign in the next year or two to have airborne LiDAR data acquisitions here, and using the Elvis data system, which can cover really large area in a short amount of time. And that should be kind of a starting point of enhancing the work in Southeast Asia. And number two, from my personal perspective, I would like to see how the profiles, the L2B product, which I'm leading, being better integrated into both the terrestrial ecology community as well as the satellite observation. Right now, the L4A, the biomass, is generated only using the L2A matrix, the height matrix only, while the L2B, including the canopy cover, leaf area index, and this vertical profile, are more ecologically meaningful and somehow be directly measured from the ground. And if we can do so from the ground, then we do not have to rely on the precise geolocation requirements in GEDI, which is always tricky. And for your information, GEDI still has geolocation around 10 meters. And this might not be too bad in terms of how poor the common GPS we have in the forest. And anyone who's walking in the forest know how terrible it is to do that in a deep forest. 10 meters kind of common thing. So if you have like two completely missed like plots and trying to do that to do a decent calibration, I would say, well, good luck, right? So we somehow need a more biophysical transferable model to do that. And I believe the L2B and the terrestrial lidar is the future. And on top of that, the third element I've already mentioned is like, it always involves the stratification, meaning how well you really want to do regional and how well you want to do global. Because if you go to find a model within region and did a very good job just in Southeast Asia, that does not necessarily mean it's useful global wise, especially when we're trying to talk about the transferability and the transparency. And as far as I know, European Space Agency is trying to develop its own protocol. NASA is trying to develop its own. And I don't see much being done in this region. And there should be some work to be done to make sure there's somehow a voice from Southeast Asia.
Thanks so much.
Thank you, Dr. Tang. Dr. Tang, so for maybe researchers or organizations who wish maybe to contribute, is there a standard protocol or a format maybe for the data sets, especially coming from plot data sets that people can use if they want to collaborate or contribute to the GEDI mission, like especially in Southeast Asia, where there's still, like to reduce uncertainties, right? Yeah,
absolutely. So I guess this comes in two components. The first one is for the, as I mentioned, the calibration component. For that, it is kind of a contribution to the real GEDI database, and that can inform and help improve the GEDI. And for that, we usually require a simultaneous acquisition of the field data and an airborne LiDAR data, because that's how we generate the simulated GEDI waveforms and the equivalent signals, such that we can generate a biomass prediction. But on the second component is the validation, the post-launch validation component, and it's still in development, that we hope to get more data to help us better stratify the information of GEDI and ultimately generating kind of a customized estimation. It's community-based, I would say, a crowdsourcing efforts of doing that. And we do have a protocol for doing this. It's all hosted by and approved by University of Maryland and Goddard Space Flight Center. And there's also data sharing agreements, meaning that the data is still owned by the data owners. And with their consent, we use this to help build the mission, but we will not distribute it to any third parties without agreements. So for example, in that we have both public version and the private versions. Public version is just open to all.
All right. Thank you, Dr. Tang. Any questions again from our audience? Okay, so I think that's all the time that we have for today. Thank you to Dr. Tang for taking the time to share your work, and thank you all for your active participation and questions. Before you leave, we would appreciate your kind help in filling up our feedback form in the chat. It will also be sent to you by email. So thank you, and we hope to see you again at our next webinar.